Optimization of plant layout for small and medium-scale industries. Abstract: to sustain in today's economy, manufacturing plants must be able to run efficiently and respond quickly to changes in the product mix and demand. The efficiency can be improved by improving various parameters, i.e. reducing transportation distance, reducing waste generated during process, utilizing manpower, reducing energy consumption by improving manufacturing method, etc. In this proposed method, optimization is achieved by reducing the material handling distance by modifying SLP, systematic layout planning, method using previous production data. This method is useful for small and medium-scale industries which have various manufacturing flows based on the customization demand. As a case study, a medium-scale industry manufacturing PP, polypropylene, bags is taken under consideration. 1. Introduction. Planning the layout at the outset before building the plant or office is the best way to reduce the costs remarkably. Producing products or delivering services at high quality, with less cost and in short time using the fewest resources is the objective of properly managing a facility too. Following are the main aspect of the research. For this research, Vishwa Industries has been chosen. Vishwa Industries are the manufacturer and exporter of woven sack which are useful for packaging of grains, sugar, fertilizer, jaggery powder, and cement, etc. The manufacturing unit mainly consists of warehouse, tape plant, loom machine, laminating machine, gusset machine, testing machine, BCS machine, printing machine, liner inserting process, stitching, baling and storage. Following are the processes explained which are useful for understanding the paper. Fabric roll from the warehouse is set up on the BCS machine. The roll then cut into bag of required length and then stitched at the bottom of the bag. Every bag has to go under this process. Capacity of the machine is 30 to 40 bags/min. A 3-color printing machine is used in the plant. 1 bag at a time is fed to the machine. Worker collect colored bag manually and make a pile of them. Coloring is not mandatory process as it depends on the customer's requirement. Liner is the thin polythene bag which is inserted in the PP bag manually by a certain mechanism. Many times customer demands for the liner. Liner bags mainly required for the jiggery plant as liner prevents moisture to enter in the bag, hence keep it for long time. Stitching at the top of the bag is done to increase the strength. Sometimes customers don't ask for stitching as it is not required for the purpose. Also, bags without stitching costs less. Baling is the process of pressing bags, generally 500 or 1000 bags at a time to make mass compact, hence less space occupied for storage and easy to transport. The industry manufactures PP bags based on the customer requirements. Following are the various requirements of the customers. 1. Printing and liner and stitching. 2. Printing and liner. 3. Printing and stitching. 4. Liner and stitching. 5. Only printing. 6. Only liner. 7. Only stitching. 3.1 Study of existing layout. 3.2 Layout planning. Several facility planning techniques could be used to develop a new layout or improve the current layout, such as systematic layout planning, SLP, pairwise exchange method, PEM, graph-based theory, GBT, dimensionless block diagram, DBD, total closeness rating, TCR, etc. In this study, SLP facility planning methods have been used to design the sustainable layout. 2. Problem statement. In systematic layout planning, SLP, it is difficult to determine layout/flow of process when relationship chart gives same closeness for more departments. Hence, to modify relationship chart to optimize material handling distance, when the plant departments have same closeness. 3. Methodology. Figure 2, Existing layout. Figure 2 is the existing layout of industry, which have 2 sections. First is fabric making plant and second is bag converting plant. In the bag converting plant, customized bags are made according to order. In layout planning, SLP technique is used. Rel chart is used to develop the relationship diagram and the space relationship diagram. For this study, both are shown in Figure 3 and Figure 4, respectively. Figure 3, Relationship chart. Where alphabets represents closeness as follows: A equals absolutely necessary. E equals especially important. I equals important. O equals ordinary closeness. OK. U equals unimportant. X equals undesirable. 3.3 Result evaluation. From Figure 3 and Figure 4 it is clear that BCS unit has to place at the center as is most important, and second importance is given to baling machine as every product has to go under this process. Now, due to layout constraint, stitching, liner and printing departments has to place one after another, but the problem is stitching, Printing and liner departments have same closeness to the BCS unit, see Figure 3, so there is uncertainty of placing these departments closer to the BCS unit. This uncertainty makes layout planning complex. As stated in the problem statement, to optimize material handling distance, when the plant departments have same closeness, modification of the relationship chart has to be done to clear out uncertainty about layout. 3.4 Modification. So, as to clear out uncertainty, relationship chart is modified on the basis of previous production data. Since the industry has started in 2016, from then it required an average of 720 tons of material every year. The material is in the form of plastic granules which then processed throughout the process. Table 2 shows the percentage of the weight transferred through various process throughout the year. At an average of 100 kilograms of material, nearly about 1,000 bags, i.e. one lot is moved at a time from one department to another. Table 3 shows the distance traveled by the material before optimization for each customized process throughout the year. To obtain optimized layout, the modified relationship chart is used. In modified relationship chart, average percentage weight traveled through various customization from Table 2 is used. The closeness value and average percentage of material weight is written in the same block. Figure 5 shows modified relationship chart. From the above figure, adding percentage values as a normal value for individual departments. Printing equals 7.7 plus 10 plus 12.9 equals 30.6. Inserting liner equals 10 plus 3.12 plus 12.9 equals 26.02. Stitching equals 25.9 plus 12.9 plus 19.3 equals 58.1. The above data clearly shows that maximum value is for stitching department and minimum is for the liner department. Maximum, the value maximum is the material flowing through the department, so having stitching department first to the BCS machine and liner inserting department last will decrease the material handling distance, i.e. optimize the layout. Using this information, modified layout is proposed, see Figure 6. For result and discussion. In the modified layout, see Figure 6, position of 3 departments is altered as to obtain optimization. After modification, the material handling distance changes for each customization. The table, see Table 4, shows the material handling distance after modification. Table 4, distance traveled after optimization. Once getting material handling distance for each customization, the total material handling for a year is calculated, see Table 5. The total material handling distance before optimization was 304,864 feet, while after optimization is 257,734 feet. There is reduction of 15.45%, which is equal to 47,130 feet. The reduction in the material handling distance eventually leads to reduction in material handling time, hence, increase in the productivity. 5. Conclusion. The goal of this study is to develop a new production layout for a PP bags manufacturing industry in view of the need to increase the production capacity using facility planning and design techniques. The first step is by using SLP method, relationship chart and relationship diagram are obtained. Evaluation is done to check whether optimized layout is possible or not. If layout cannot be optimized, then modification of relationship chart is necessary. The evaluation shows that due to some constraints the optimization based on the regular method is not possible. The new layout obtained after modification of relationship chart using previous year's production data gave optimized layout. In optimized layout there is reduction of 15.45% in material handling distance throughout the year. 6. Future scope and disadvantages. When relationship chart gives same closeness to more departments, then it is difficult to decide flow of material. Thus, modified method is used when regular method fails to optimize layout. The main disadvantage of the modified method is industries need to have previous year's production data, without it modified method cannot be used. Another disadvantage is, this modified method will not be effective when previous production values shows more fluctuation.